In this video, I want to introduce you to power series. Um, this course does not have a prerequisite of sequences and series, so it's not assumed that you know about power series yet. Some of you may have already done this. But for those of you who don't, Section 5.1 is a crash course in power series. And because we will be using them in subsequent sections here to, well, help us solve differential equations. So here's some terminology, and we will uh, get you familiar with power series before we use them. A sequence, first of all, is an infinite list of numbers. So I have a list here: 1/8, 1/64, 1/8 cubed, 1/8 to the fourth, and so on. This is the dot 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 is saying continue this pattern forever, right? So the next one will be 1/8 to the fifth, and 1/8 to the sixth, and so on. Sometimes I would abbreviate this as the sequence a sub n, where a sub n is equal to 1/8 to the n. So I could tell you what the 100th term in that sequence is by plugging in n equals 100 and seeing what it is. Now, sequences don't have to be nice and orderly like this one is. They might just be an infinite list of random numbers, right? That would still be a sequence. It might be hard to write down a formula to describe what the nth term is, not the nth term, but the nth entry in the sequence, then, but that's fine. We will generally be dealing with ones where you can write down a formula to say what the nth term is. Now, so a sequence is just a list of numbers. A series, on the other hand, is a sum of that infinite list of numbers. So it's the sum of an infinite sequence. So for instance, 1/8 plus 1/64 plus 1/8 cubed plus 1/8 to the fourth plus 1/8 to the fifth, and so on, is a series. It is a infinite sum of numbers. This is quite often denoted using the summation notation. You've probably seen some summation notation in like a Calc 2 class when we're first learning how to do integrals, estimating integrals, and Riemann sums, right? So this means this symbol is the capital letter sigma, which is the first letter of the word sum in Greek. So if you want to add stuff up, and we give an index, the name of the index is n, and then you give it a starting value and an ending value. Now with a series, the ending value is infinity. You just keep going forever, right? So what this means is you're going to take n, start with n equals 0, plug it in, figure out what an is. Then take n equals 1, plug it in, figure out what so first of all you figured out what a0 was, then you figure out what a1 is, and then you plug in n equals 2, and n equals 3, and you keep getting a bunch of numbers, and you add them up. The sum means add up all these numbers. So this is an infinite sum of numbers where the ANs are calculated in some way. Now, for instance, if I use the AN equal to 1/8 to the n, I might be looking at a summation like this, and this is the summation form of this infinite series that we had listed up above here. Now, I have to admit that this series is of significance to me because it reminds me of my childhood and eating ice cream. I will explain eventually. Now, how do you actually add an infinite sum? How do you add an infinite number of numbers? And the way we do this is we don't. We add a finite sum. We say, okay, stop at k. So n equals 1 or 0. You may notice that the starting point is changing. Sometimes it's a 0, sometimes it's 1. It could be anything. You could start at anything. It just depends on what you want to do. Now, since this one right here was started at 1/8 to the 1, my starting n that I wanted to plug in there was 1, so I started the summation at 1. As we'll see, you're going to get different starting things, and sometimes you're going to want to adjust what the starting value is. And anyway, that's all coming up in future videos. Anyway, to do a summation here, from your starting point, go to a finite ending point, k. And since it's only a finite number of things you're adding up, then you can do that. That will be a finite number. Okay, and then we're saying take the limit as k goes to infinity. Look at what happens when you add up the first 100 terms, 101 terms, 102 terms, 103 terms. Look at that sequence of summations and see if that sequence has a limit. Sometimes the answer is yes, it does, and sometimes the answer is no, it doesn't. And the no, it doesn't could be for many reasons. One could be that it's adding up to bigger and bigger and bigger, and it just goes up to infinity. It might be that sometimes you're adding positive numbers in and sometimes you're adding negative numbers in, so that the sum, the partial sum here, this is called a partial sum when you start at k, the partial sum when you stop at k, the partial sum might grow to some value, but then as k gets bigger, it might then come back down again to some other value and then grow back up again to some. So it may not actually go to infinity, but it might not settle down to a particular value. So that would still be not adding up to a number. If there is a limit here, then we say that the series converges and that the value of the limit is what the summation adds up to. If that limit does not exist, then we say that the series diverges. Okay? And now the next video we'll look at how we test for convergence or divergence of a series. Okay. One particular series that is used quite often, and we will use it in these upcoming videos, is what's called a geometric series. And a geometric series is essentially one where each term in the sum is obtained by multiplying the previous one by the same thing. So if the first term in the summation is c, and I multiply by r to get the next one, then I'd multiply by r again to get the next one, and I multiply by r again to get the next one. So this is what's called a geometric series. It's just a constant times r to the n, where n goes from 0 to infinity or 1 to infinity, whatever. The way I have it written here, I'm starting off with it at 0 because my first term has an r to the 0, which is 1, and it's just c. And my computer is interrupting. So a geometric series looks like that. This series that we have right here is a geometric series. The initial term is 1/8, and then you multiply by 1/8 to get the next one, and you multiply by 1/8 to get the next one, and so on. So this would be an example of a geometric series. Now, the purpose of this video is really to say what is a power series. Now, a power series is a series, so it's an infinite sum, but there's a variable involved, and that variable is raised to bigger and bigger powers each time. It's essentially an infinite polynomial. Okay, so here's an example written out where it starts with a constant, and then you've got some other constant times x minus x0 plus another constant times x minus x0 squared, x minus x0 cubed, constant times x0 to the fourth, and so on. In summation notation, it might look like this. The sum n equals 0 to infinity of a sub n times x minus 0 raised to the n power. Okay. Notice that starting at 0, anything raised to the 0 power is 0, with one small exception which we overlook here, that because 0 to the 0 power is an indeterminate form and it could be anything, but for now it's going to be 1. 0 to the anything else to the 0 power is 1, so plugging in an n equals 0 here is just giving us that a sub 0. Okay. This power series is what's called a power series centered at x0. And when we look at convergence in the next video, we'll see why that word center makes sense. Centered at x0. Okay. Now, quite often, the x0 is just 0, and this just looks like an times x to the n, because this is just a 0. But, like, for instance, here's an example. And this is a function of x now, right? This depends on what value of x you plug in there. So I'm going to say f of x is equal to this example, where I've got 1 over 8 to the n, x to the n. For some values of x, this sum is finite, and for some values of x, this sum is infinite. It diverges, right? For instance, if you plug in x equals 0, this would be, 0 to the n. I don't care what n, whether you raise it to the first power or raising it to the 0 power is an issue. But actually, this sum I'm starting at 1, so I'm not going to do 0 to the 0. But they're all zeros, and so I've got a sum of 0 plus 0 plus 0 plus 0 plus 0 infinitely many times for a grand total of 0. This definitely adds up to 0. In fact, all of these power series, if you plug in x equals x0, then each term in the sum is 0 and it converges. It adds up to 0. So each one of these power series has at least one value of x where you get convergence, and that value is at x0. Then there's a matter of, are there any other values where it adds up to x0? Well, here with this function listed as it is like this, if I plugged in 1 for x, then this would be 1 over 8 to the n times 1 to the n. Well, 1 to the n is always 1, so this just looks like the sum, as we had it listed before, 1/8 plus 1/8 squared plus 1/8 cubed plus 1/8 to the 4th, and so on. And actually, I am starting at 1, so it does start off at 1/8. And that adds up to 1/7. Very quickly, here's the reason why it adds up to 1/7. We were having ice cream one night when I was a kid. I'm one of 6 kids, and Dad was having ice cream as well. For some reason, Mom wasn't. And we had this half-gallon block of ice cream that Dad took out the big knife and cut it into 8 equal pieces and handed us each a piece. So there were 7 people eating ice cream. So there was 1 piece left over. We each got 1/8 of the ice cream on that first round. That 1 piece that was left over, Dad cut into 8 equal pieces. And we each got 1 piece, and so there was 1 piece left over. And of course, you could then keep doing that in theory. Of course, it just turns to mush after a while. But in the first round, we got 1/8, and in the second round, we got 1/8 of 1/8, and then the third round, we'd get 1/8 of 1/8 of 1/8, right? So the total amount that we would get would be 1/8 plus 1/8 squared plus 1/8 cubed plus 1/8. This is precisely this summation right here. And he asked us, how much did each person get? Now, I don't know how old I was. I might have been 10. I don't know. But he had shown me how to add geometric series up before, and I'll show you in the next video. So I was about to go and do that. When my younger sister, who's 2 years younger than me, so if I was 10, she was 8, she says, well, we all got the same amount, and it's all gone. So we each got 1/7. Yep, she was right. We each got 1/7. That the summation, that infinite sum, 1/8 plus 1/8 squared plus 1/8 cubed, and so on, is equal to 1/7, finite number. Okay. Now, one more example that I want to throw in here is if I plug an 8 in for x, still looking at this same function here, plug an 8 in, then the 1 over 8 to the n times 8 to the n, the 8 to the n's cancel out, and what I'm looking at is the summation of 1. That is, each term in this infinite sum is a 1. 1 plus 1 plus 1 plus 1 plus 1 plus 1, forever. What does that add up to? Well, it certainly doesn't add up to anything finite. I can show that that's bigger than any finite number, so it must be infinite. This diverges, right? So for some values of x, 0 and 1 for instance, this summation converged. But for another value of x, it diverged. And so the question that we'll have to look at for the next video is, what can we say? Can we predict what values of x will make it converge and what values of x will make it diverge? And the answer is, we can say quite a bit, and we will.